I think I might try to risk it and maybe wait 1 minute for people to come in. Is anybody here loud enough? You, go outside and yell, people go into Hall A. Do it now. I'm serious. She's my friend, don't worry. I'm not just using a random person to go and do it. It's just what? The random girl that I never met. You go outside and shout everybody to Hall A. But for now, we can just maybe look at images of my dog. I was prepared for this moment where we would have a delay in Hall B, and we would all look at images of Ginger. So let's maybe start by introducing myself until everybody comes here, because who am I is probably the least important part of the talk. So I'm Ariel. I'm a full-stack developer at Illumex. I am a public speaker, quite obviously. I'm here. I'm very enthusiastic about dogs. This is my dog, Ginger. She's a backend developer. Woo, Ginger! Ginger and I are hiring a senior Python developer for our team at Illumex. So if anybody has any friends that for some bizarre reason enjoy coding in Python, so just tell them to come to me and I will help them. They would get a warm cup of tea, maybe therapy, and a job. I think I'm not gonna wait that long. Okay, we will just maybe start, and they're lost. So we are going to be building a social network today with Node.js and Neo4j. It's going to be quite an interactive session. So you guys are going to be taking part in this talk, and it's going to be very, very fun. I do hope the Wi-Fi gods will be on our side here, because you guys would need to connect to the internet. I think I'm just going to start, unless somebody wants to hear more details about Ginger's early life, career choices, and previous jobs. OK, we are just going to start. So we are going to be using Node.js that I think you guys know, and we're going to be using Neo4j. So Neo4j is a leading graph database platform for enterprise scale. I am a production user of Neo4j, so that is the reason why I chose Neo4j for this talk. I imagine some people here might have used Neo4j. I imagine some people here might have experience with graph databases. I imagine some people here have never used a graph database, so they probably haven't used Neo4j if they have. So the first part of this talk would be talking about just explaining graph databases and kind of the problem that they solve and the cool questions we can use graph databases to answer. And in order to discuss graph databases, we need to start kind of at the basics. And we would want to start by discussing what is a graph. This is an interesting question, the question, what is a graph? And I have a few takes on this one. So the first formal take on the question, what is a graph, is the mathematician's take. If you ask a mathematician, what is a graph, mathematicians would tell you that a graph is a structure of objects in which some pairs of the objects are in some sense related. So the objects correspond to mathematical abstractions called nodes and relationships, or you can call them links. And we have very, very cool algorithms from the world of graph theory that these algorithms can really help us a lot in our day-to-day lives. And these algorithms actually already help you a lot in your day-to-day lives. You just might not be aware of it. And you are going to be learning today about how many things around you, how do they really work with graphs. So that was the formal take. But I think that in order to discuss graphs, you really can't avoid visualizations. Like it's a critical part in understanding what a graph is. So this is the second take, the visual take. This is a graph. This is how a graph looks like. And as we said, graphs are composed of two types of objects. So the first object is nodes. The second object is links or relationships. And an easy way to wrap our heads around it is understanding that the nodes are the content and the links or relationships are the context. This means that we can have a node that's floating in space. It has no links connected to it. But we cannot have a link that is not connected to a node on both edges of it. So I think we are starting to understand graphs. And we answered what is the formal take on what is a graph. We answered with a visual take on the question, what is a graph? But I would like to share my personal take on the question, what is a graph? Because if you ask me the question, what is a graph? Then I would just answer, well, everything. As a matter of fact, this whole universe in which we are living in is nothing but layers over layers over layers of graph. And it doesn't matter which dimension of the universe we would try to explore, we would see layers of graphs in every single dimension and on every single layer. So if we try to describe space, and we start at the top level. At the top level, space is a graph. The stars are the nodes, and the forces between the stars are the links. But if we go one layer lower, our own planet, our transportations are also graphs, graphs of intersections and roads between them that are the links. It's a two-dimensional graph. And even if we go lower than that to our own bodies, our own brains are a graph. Our brain is a graph where the nodes are the neurons and the synapses are the links. But even if we go lower, the molecules that compose our brains are also graphs. They are graphs where the atoms are the nodes and the chemical bonds between the atoms are the links. And, as a matter of fact, atoms are also graphs. Graphs of protons and neutrons and electrons. And some people would also say that when you try to go lower, it would all kind of just start over again. And what if we try to describe time? Time is also a graph at any single layer that we choose to explore. Our ancestor tree, a tree is a specific use case of a graph. And even if we go lower trying to describe time, our own DNA is a graph. And as a matter of fact, describing the changes in this graph, in the graph of the DNA, that's literally a way to describe our evolution. And even if we speak of less existential topics, and we talk about code, even code at every single layer is a graph. When we speak about networks of different microservices, or even when we go lower to version management, this is a slide from my talk about Git, and Git is also a graph. It's a tree. As a matter of fact, Git is the ancestor tree of our code. And even if we go lower to the code itself, this is a slide from my talk last year at the Node.TLV when I talked about TypeScript. So when our code is compiled, it is parsed into a structure called AST. AST stands for Abstract Syntax Tree, a graph. Who's feeling like this cat? I'm feeling like this cat now. So after the philosophical take of the question, what is a graph? I think we can start discussing graph databases. Let's start with a brief history of databases. So databases started forming in the 1960s, but it wasn't really until the 80s when a model that's kind of similar to what we know today, when the relational databases kind of started appearing and pretty similar to what we know these days. So the 80s kind of mark the beginning of our timeline, okay? The 80s are the beginning of relational databases era. And relational databases are awesome. I think MySQL, up until today, is the most used database. And we would have stayed with relational databases if not 10 years later when the world changed. When Tim Berners-Lee gifted us with the World Wide Web. And suddenly, we were introduced to scale to scale that we couldn't imagine before, when you have suddenly millions and billions of humans and devices creating data and updating data. And the relational databases were kind of architectured around this idea that a database is going to live on a single machine. And we were reaching scales that were not fit for a single machine. And this kind of led us to the next era, the era of NoSQL databases. By the way, NoSQL is not NoSQL. It means not only SQL. So it can handle both structured and unstructured data. And 6 years later, Tim Berners-Lee does it again. He publishes a paper called Linked Data, which is going to be later on the base for graph databases. You might ask yourself, why did we need a third type? Why do we need graph databases? And to answer that, we need to focus for a second on the differences between relational and NoSQL databases and what are they good for. So relational databases are pretty good when we have nested data because we are defining our schema in advance. It allows us with SQL to query data that is very, very deeply nested. NoSQL databases are good for unstructured data when our schema keeps changing, but it's less good when we have nested data in performance-wise. The problem was that, as we saw at the beginning of this lecture, this world is both deeply nested and both unstructured. So we kind of needed a third type. We needed something that could answer questions that could not be answered before. So if you try to, for a moment, compare the abilities of these three, so as we said, relational databases are not really good with unstructured data. Like, you can save JSONs in a Postgres, but like, just because you can, it doesn't mean you should. It's not optimized for it. Graph databases are quite good with unstructured data. Obviously, they are still a NoSQL database. And obviously, NoSQL is good for unstructured data. So SQL, pretty good for nested data. So is graphs. And NoSQL is less good when we talk about that. And last, I'm talking about a learning curve. But when I say learning curve, I don't mean how long would it take a junior to write one line of code. No. I mean the learning curve as an architect, the learning curve in scaling a database like that, in designing our data, in modeling our data, so that for years on, our database is still performant. And in this case, I feel like relational databases are. It's hard to make them scale for a long time. As someone that used to work in a bank, and I've seen a relational database that lived for 40 years, trust me, don't. Graph databases are also challenging in modeling, and mistakes are pricey. I feel like NoSQL is kind of the best in the terms of a learning curve, and as in scaling this data for a long time and modeling it. It's a bit easier. So the reason for the performance differences is because when we use NoSQL, we kind of need to be jumping between collections to get nested data and to go over collections. That's less efficient. So SQLs are pretty good for nested queries, but we don't always know our schema. That's how life is. And graph database is kind of giving us the ability to enjoy both worlds. We don't need a schema, but we can deeply nest our data. Let's start. I think that you understand why do we need graph databases now. So we're going to start with the atoms of this. Let's imagine that we have a database and we have two types of entities. So we have humans and we have a house. So let's say that in our case, this human would be a human named Ariel. Her birthday is in June. It might be in 4 days. She likes expensive presents, I'm just saying. And let's say that she lives in this house. It's not really this house, don't try me. And what would be how would I describe that Ariel lives in this house in a NoSQL database, in like Mongo, for example? I would need to either add a reference to the ID of the other entity, or I could even choose to populate it maybe. But even when I populate, like, I'm kind of limited in how much could I do this, how deeply could I nest, and how much do I even really want to nest data into a single document. And graph databases kind of solve this, in my opinion, in a really nice way, because the content stays agnostic. So I don't need, the data of a human is just relevant to the data of the human, and the connections are, all of its relations are a different entity. So my way in a graph database to say that Ariel lives in this house would be to create a link that would be connected to Ariel on one end and connected to the house on the other end. And I would label this link as rent. So in graph databases, labels are the main index, okay? That's kind of like saying what table is it from. And what's cool here is that I can use this link and save even more data regarding this relation. So I can say that, for example, my contract ends in 2025. To do this in any other database, I would need another entity that would be kind of the connection between them, so a linking table. I think we got it. I think we understand how nodes and links work. And we can start speaking of like the full picture. So traversals. Traversals is the word for querying a graph. And as I said earlier, graphs have very cool algorithms that could be used to answer cool questions. So when I'm traversing the graph, I could be looking for quite a few things. So I could be looking for data in the graph, but I could also be looking for patterns or paths or groups, and we'll get into each. So looking for data means I can ask the graph questions that I can ask any other database, okay? I can ask any other database who are my friends. This is not impressive. What's cool in a graph is that I can ask also who are my friends' friends, or my friends' friends' friends, or my friends' 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 friends. It's actually, to a finite number, I can ask levels and circles of people that I know. And that's how LinkedIn works, for example. When you see a person on LinkedIn and it tells you what friend circle is he from, they're using graphs to do it. And to do this in any other database, it would be somewhere between slow, challenging, or just inefficient. So this is what's called subgraphing, okay? To take a graph, a sub-part of my original graph. Another thing I can do is look if I have some patterns that are happening in my data. So for example, I could be asking my graph, are those two people linked somehow? This ability, for example, is used a lot in cybersecurity, in the detection of fraud networks. And this is something I can't ask any other database, because it would be a Cartesian product of a lot of properties that I would need to check from. And with a graph database, I can just do it with one single easy function. Another thing I can use a graph database for is to look for a path, or specifically the shortest path. So I can ask a graph database, what is the fastest way from my house to my house from the station? Because as we said, our transportation is also a graph. So this is how any navigation application that you use works. They actually use the graph algorithm for finding the shortest path. And last, we can use a graph database to ask what are the friend groups in this room. So clustering algorithms. This is a really cool ability that I use personally a lot at work. And you can cluster by a lot of different parameters, and it's just very cool. So let's build a social network. Our requirements for today, so we want a user to be able to add his friends, to see his friend circles by level, to find the shortest path from one user to another, and to see who are the most connected people here in the crowd. So I thought this hall would be full, but I'm actually happy because you might have enough Wi-Fi for the demo to work. Let's start by describing what model we're going to choose. So we're going to have a person. No, that's the node, the only type of node we're going to have. A node of a person, that's the label. And the person could have a few properties. He would have an ID, a name, email, generation. I wanted to have age, but then I thought it would be offensive. So just have it less offensive and write what generation are you from. And where are you from, where are you originally from, and what company do you work at, and what is your stack. So this is our model. Very simple, one entity. This is its type, super easy. And our way to describe friendships is throughout links of friendships. So between different people, we would have a link that it's a link of friend of, and that is basically all we need. It's going to be like 5 functions in a service to create a social network that does all of this. Let's try. Let's see how the internet goes. I'm going to be doing this with you because I thought this was a simple task, and I did a similar demo at a lecture, and apparently it's not that easy. So I'm going to be doing it with you, hand by hand, hand in hand. Let's open some Wi-Fi for me. So my internet is not working yet. OK. So try to not use autocomplete, because the autocomplete is annoying with that the component that I chose. It was a bad choice. Let's do it together. So I recommend to write your real name, because your email doesn't have to be real. But I recommend to write your real name because I think we can add each other on LinkedIn later, which can be nice. I'm a Gen Z. That's very humiliating. So I live in Tel Aviv. I grew up in Tel Aviv. I know I'm one of those. I'm full stack. I work at Illumex. And on the next page, if you don't see your friends there right away, then just keep refreshing. Let's see if my friends are here. Evyatar, I'm going to add you. You have 2. Is it the last one? Yoni, I'm going to add you too. Noam, I saw you're here. You didn't sign up yet. You're signing? Let's see if my friends are here. Polly, no? Girls, you needed to sign up. Okay. I'm going to go with Evyatar and Noam and Yoni and Shkoler. Who else is my friend? Imri, I don't know if you signed up. You didn't sign up, Imri? Lame. Nitzan. Bibi Netanyahu. You're not my friend. איפה ג'ינג'ר? מי רשם את ג'ינג'ר? Sorry, English. That's enough. I don't have much more anyways. לא מצאתי אותך, מה אני אעשה? Okay. Guys, so many people here alone. Who signed up twice? Well, it's my bad doing a POC live. But this one is pretty cool. This one is even better than what I imagined would be. We have a demo data just to be safe. But let's maybe keep refreshing, see if people are adding each other. Okay, I have 6 minutes, so we are just going to be going over this data that we have. So we are going to be using this data of the people in the crowd to be demonstrating different algorithms of graphs, okay? So we are going to be using, for example, the first algorithm we're going to check is the algorithm for the shortest path. So we are going to be looking for the shortest path from Evyatar to, let's look for someone interesting. Well, Bibi Netanyahu. Guys, you're so funny and clever. I cannot. Ah, a direct friend. How surprising. How surprising. Let's look for your relation to Yuval Shkoler. Oh, I'm a friend of, we're both friends of each other. So we can see that it's basically how any navigation app works, okay? This is exactly the properties that would be, this is exactly the functions that would be used. And what's really impressive is how easy is it. So this is a cipher in the database, and I would only be needing to check what is the person I'm going from, what is the person my target, and then just a simple function, shortest path, and I can do something that no other database can do, and surely not with one single line. Let's try to find a subgraph. So I'm going to be looking for, this is actually something that I'm just curious to see. I'm going to be looking for my friends' circles, okay? So I'm going to be trying to subgraph all the people that are my second degree. And what I can do is to see who are you guys. Wow, I have a lot. And I can just be opening a profile of each. Let's see. Who's my second degree friend? Aviatar? Ah, it's the old one. Ilya. Who's Ilya? I don't know who you are, but let's be friends. Add me on LinkedIn. So you can just open the profiles and add people. You have like this copy button for our names. And our last algorithm would be an algorithm of what's called between-us centrality. So between-us centrality, that's a really interesting one. I knew I would win. Ah, I didn't win. Aviatar won. Let's start with what does between-us centrality mean. Okay? Between-us centrality is an algorithm that allows us to calculate what is the most centric node in a network. So for example, if we have a transportation network, then the main train station would probably have the highest between-us centrality scoring, okay? It's a way to score how central is a node in a network. So Aviatar in this case is the one with the highest between-us centrality here, actually, this one is kind of interesting. I want to show you how does between-us centrality look in the graph that I prepared before. So we have backup data, if anybody is keen to check that one out, with a lot of famous people. And when we look at the between-us centrality in this graph, it's quite surprising, because you would kind of expect somewhere here to have the point with the highest between-us centrality scoring, but it's actually, it would usually be an intersection that connects different intersections, because it's measuring how many shortest paths go through a point. So usually it's actually the intersections between different ones. And this graph is actually pretty funny as well, because I gave a lot of famous people, I gave them jobs. So I gave Uncle Bob a job at Amazon. I don't know if Amazon would want Uncle Bob there, but he lives in Petach Tikva, but he's originally from Netanya. He is a baby boomer. This one, sometimes demo data is right. And he somehow got accepted to Amazon. So, very not PC of me. Okay, let's go over what we did do. If somebody wants a link to the repo, then you can scan this one, or just text me, call me, write to me on LinkedIn, and I would send you, and I can go over the repo as well, because there are more things that I didn't have time to go through in this talk. So what's very cool is that it takes very little code to do something that no other database could do with so little code. So being able to see your friends' friends by levels by degrees of how close you are to them, or to find what's the shortest path from one person to another. And yeah, just to be able to measure how central is a person in a data set. These are very cool abilities, and I hope that you learned some new things. So thanks a lot. Thank you. And I'm looking for a senior Python developer. Please help me. Thanks, guys. Enjoy lunch.